Hi, we're going to do 5.3 in your algebra, diagonalization. So in our previous work, what we had were some theorems that we kind of skipped over, but we need to address them. Proofs are in the book. So theorem number 2. If we have a set of eigenvectors that correspond to distinct eigenvectors, lambda 1, lambda all the way up to lambda r, of an n by n matrix A, then the set of those eigenvectors is linearly independent. This is what's going to be necessary for us to achieve what we want to do in this section. The proof is proof by contradiction, which is a good technique to learn. That's in the book if you want to check that out. And then Theorem 4 is another one. If n by n matrices, A and B, are similar, that's the key word, then they have the same characteristic polynomial and hence the same eigenvalues, also with the same multiplicities. And if this is the case, if both are similar, then there's an invertible matrix P such that A is equal to P, B, P inverse, or equivalently B is equal to P inverse AP. So you can work back and forth. We've done a video with some of that, but that's just kind of working from one space to another space, so to speak. Now this theorem does not work the other way around. If you have the same eigenvalues, that does not mean that the matrices are necessarily similar. Also, similarity is not the same as row equivalent. Row equivalent matrices will probably not have the same eigenvalues. Okay, so let's start off with this. Example 1 says, given that we have a matrix A and we want to know if we have a situation where A is equal to P, D, P inverse, find the simplified form for A to the fifth. And so what we want to see is what happens when we break this down a little bit. So if we set this up, we have A squared. So if I do A squared, I'm just writing this thing twice. And when I write this thing twice, what I'm also doing, I can do the associative property and group the P inverse, this one here, and this one here, group them together so that they're going to go ahead and cancel out. And when I do that, those cancel out, and look at the B's. The B's match up here. Well, what's B times B? That's going to give my B squared. So really, in other words, when we square these things or raise them to higher and higher powers, all that's going to happen is that these two middle ones are going to drop out, and so we're going to be sandwiched in between P and P inverse for this. And the only thing that's going to be raised to the power is going to be the inside matrix. And so if I want A to the fifth, I can continue on with this, dot, 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 and then I get A to the fifth is equal to P times B to the fifth, P inverse. Okay? This helps our calculations, minimize our calculations, all those kinds of things. It also shows us how we can use diagonalization a little bit. Moving on to example 2. If I give you D is equal to this matrix right here. Now this is a diagonal matrix. And it says diagonalized, but it's actually diagonal matrix. With this, I want to see what are the patterns to get to D to the fifth. So I'm just going to punch this into my calculator repetitively and see what happens. So I'm going to go D squared, D cubed, and so on. So if I do that, what happens? Well, the entries just turn out to be raised to that same power. So D squared means that the 1 will be squared, and then the 1/2 will be squared. D cubed, same thing. And so this is just 1/2 to the third power, 1/2 to the fourth when we do D to the third, and 1/2 to the fifth when we do D to the fifth. Okay, that's going to happen for any size dimension diagonal matrix. So you have zeros up on top, triangular, zeros on the bottom, triangular, and so overall it's just the diagonal that we do have. So in general, we end up with D, some diagonal matrix, and this is just for 2 by 2, but it works for all. Then D to the K is going to equal the entries raised to the K along that diagonal. Nothing else gets added. So now here's an example where I do have A and D, which are similar because it satisfies this as long as P is invertible, which it is, And so then A is equal to P times D times P inverse. So I already gave that to you, that fact. And then here's my diagonal matrix that's associated with this P invertible matrix. Now it says find A to the fifth. Well, we'll use what we did up above when we had A to the, this situation right here. So we're just going to have to raise the D to the fifth power down here. So that's what we get there. Okay, so A to the fifth is equal to P times D to the fifth times P inverse. Now, what happens? Well, I'm just going to put those matrices in. Notice that I already raised this central matrix, the D, to the fifth power. And then I have P here, and I have P inverse here. Sorry about those things popping up. I don't know how to turn them off. And then the inverse, since the determinant's 1, that turns out kind of nice, I just get this situation right here. Then I can go ahead and multiply this out and figure out what A to the fifth is. Now this might seem weird that I'm multiplying it out anyways to figure out what the values are, but if you can imagine this exponent being a lot higher and the dimensions here being a lot bigger, we're going to save a ton of computing power using this method. Okay? So it makes things a lot easier. So we want to diagonalize a matrix. And we can do that using eigenvalues and eigenvectors. So a little review for ourselves when we will go ahead and diagonalize this matrix. So this is example 4. Given this matrix, diagonalize. And so the first step says find the eigenvectors. So remember, we take this matrix and then we subtract out the diagonal matrix of the eigenvectors, or lambda, and then we can go ahead and solve using the determinant. So if I go ahead and do all that, you can do this with your CAS calculator if you have a CAS. I can find the determinant by putting 4 minus x down here, and it just happened that this diagonal is all 4s, that's why it turns out that way. Then I do the determinant, and then I get this polynomial. And then I want to go ahead and factor. Well, it didn't factor this piece for me, but I want to go ahead and factor the rest of it. So I get x minus 8 and x minus 2, along with this factor here, x minus 2. So my eigenvalues are going to be 2 and 8, and 2 is going to have a multiplicity of 2. Okay? So it's 2, 2, and 8. Now the book gives you some of the eigenvalues, so you don't have to do this. So look for that little note in there that tells you where they are. Okay? So step 1 was find the eigenvalues. Step 2 is find 3 linearly independent eigenvectors of R3, since this is a 3 by 3 matrix. And if you can't find 3 linearly independent eigenvectors, then the matrix is not diagonalizable. Is that a word? I don't know, but I like writing it. Okay, so first of all, with lambda equal to 2, and this thing, I set up this matrix and I'm going to augment it with the 0 column. Then I'm going to reduce it. Well, all these wipe out, so I'm just going to end up with the top row there. And so then with that, I'm going to end up with x1 is equal to negative x2 minus x3. I hope you can see that this would be true if these were all 1s, which they are. Okay, so now I want to put it in vector form in order to find my eigenvectors. And so I can rewrite this as x2 with this column matrix and x3 multiplied by this column matrix. And those two turn out to be then my eigenvectors for when lambda equals 2. I hope this is all review for you. If this isn't review, go back to the previous video and check that out again. Okay, now what if I do lambda equal to 8? And if I do lambda equal to 8, I take this same matrix that I had originally, and I'm going to go 4 minus 8. So that will give me negative 4 on the diagonals. So that's where it's happening here. And then it's augmented with a 0 row. So now I'm going to reduce this, and I get this situation here. So this is x1 is equal to x3, and x2 is equal to x3. So if I put that into my vector column form, I'm going to end up with this. So then I do pull this out and say that my eigenvector is going to simply be my 1, 1, 1. Okay, you might want to review this and copy this down, or hopefully you jumped ahead and did all this, but this is the process that we go through. Okay, so now I have these two eigenvectors associated with lambda equal to 2, and I have this eigenvector that's associated with lambda equal to 8. So to construct P, we use the vectors in step 2. Our order is not important. So I'm going to take the 2 that I have from it popped out a bunch for me. So then I'm going to take the vectors that I have that I found for the eigenvectors and put them all in here. So these two are from lambda equal to 2. This one's from lambda equal to 8. So the order that I put them in there is not important until you go ahead and construct D. So constructing D, remember D is a diagonal matrix. And so all you do is put the eigenvalues on the diagonal. But you must put them in this order. So it's going to be a 2, 2, and 8 because that's how I line them up in my P matrix. So order is not important here, but I do have to match it for P when I construct D. So what do I get? So this would be 2's all along the diagonal up to this one, which would be an 8. Okay? So I hope that's clear. Match these up like that. So now we've diagonalized our matrix. Are we done? Well, we probably should check. How do you check? Well, let's make sure that P times D times P inverse does work out. So I did crank this out, and you should do some of this yourself to practice. But this is my P, this is my D, and then I found the inverse of P and multiplied it, and voila. I ended up with my A matrix. So I could take this now and raise it to the power, and that'd be equivalent to A being raised to a certain power. Okay? So those are the steps that we want to go through for this section in order to diagonalize a matrix. Now there's some things that we do have to worry about. I mentioned them before, is that if I do end up with a situation where I can't find 3 linearly independent eigenvectors, and that's because you physically can't find them, not just because you gave up, but then the matrix is not diagonalizable. I can't say it. You can't find the diagonalized matrix. Maybe that's better. Okay? All right. So look for those examples in the book, and you should be sorted on that. So review those steps, and you should be all good. All right. I hope you like this video on how to diagonalize a matrix with an invertible matrix P. Thanks.